Hi, my name is Suzanne Adrian, and today we're going to talk about the propagation of an action potential down an axon. First, let's know what a neuron is. A neuron is this cell as a whole, and it contains the axon going down. The axon is where the stimulus and is where the action potential occurs. Now this neuron is made up of neuroglia. The neuroglia give it its support and its structure. Now that we know a little bit about the neuron, let's go to the action potential. This is an action potential graph, and at -70 is the resting membrane. So -70 resting membrane, and when the stimulus is given, -70 raises to -55, and at -55 the voltage-gated sodium channels open, allowing sodium ions to move down their localized current into the cell. At +40, these sodium gates close and the voltage-gated potassium channels open, allowing potassium to go down its localized current out of the cell. At -70, equilibrium is within the cell and these two gates close, allowing this action potential to end and another one to start. Now that we know what an action potential is, let's explain saltatory conduction and continuous conduction. Saltatory conduction is when an axon is myelinated. Continuous conduction is when a cell is not myelinated. Saltatory conduction has nodes of Ranvier in between each end of a myelin. At these nodes of Ranvier is where the action potential occurs. So an action potential occurs at this node of Ranvier, an action potential occurs at this node of Ranvier, and so on until it reaches the axon terminal. Now let's talk about membrane resistance. Membrane resistance is simply how resistant the membrane of the axon is. So in saltatory conduction, the membrane resistance is greater because it has myelin wrapped around it. In continuous conduction, the membrane resistance is less because it does not have myelin wrapped around it. Now let's talk about length constant. Length constant is how fast a stimulus moves across an axon. In saltatory conduction, the length constant is fast because of the nodes of Ranvier jumping from node of Ranvier to node of Ranvier. The continuous conduction is slower because it has these positive and negative charges, which makes a domino effect of action potentials moving all the way down until it reaches the axon terminal. Now let's explain the different types of myelin in the body. There is the central nervous system, which is CNS, which is made up of oligodendrocytes in the myelin. And then there's peripheral nervous system, which is PNS, which Schwann cells make up this myelin. So CNS, oligodendrocytes make up the myelin, and PNS, Schwann cells make up the myelin. Now let's go over here and talk about conduction velocity. Conduction velocity is just simply a test to show how fast the stimulus gets from the dendrite all the way down to the axon terminal. So in a saltatory conduction, when it is myelinated, which is shown here, it is much faster of a conduct velocity, and in continuous conduction, when there's no myelin, when it is a domino effect of action potentials, it is going to be a slower conduction velocity. That explains all of the action potential moving down the axon. I hope you understand everything, and thanks for watching. Have a great day.